Ahoy Captain, and welcome to the Masterclass on the average shore power demand for ships. It truly is the holy grail, determining, estimating, knowing the average power demand of ships at berth. Well, we've made up our own methodology, pretty sound one based on those of IMO, DNV and EMSA, including all the regulatory aspects, and we will provide you with all the results and the databases you need in order to make your own estimates on the average shore power demand. It is intended for project developers. What we have developed can be used in order to best estimate the revenue for a particular project. It has to be said that the methodology is especially intended if you have a multitude of ships or you don't have specific ship information, you haven't spoken to the chief engineer yet, so you don't know exactly the amount of power available. For those situations, or to give estimates across the board for multiple ships or maybe across the port, that's when you can use this methodology. We will cover the following aspects or sections in this masterclass. We will of course start with OPS, onshore power supply, shore power, cold ironing, and power demand of ships first, and why and how is there a problem. Then we will discuss our methodology and results. We will also show you the database and the guide that we have developed, and we will end with some frequently asked questions and the references we have used in order to bring you this methodology and information. But we have to start with a few disclaimers from our part. This masterclass is comprehensive but not complete. Like I said, it is intended for a multitude of ships, not one ship specifically. Plus we make a lot of assumptions on the ship itself, the drivetrain, auxiliary engines. There might be errors in the data, ships might have been changed, so we cannot guarantee that your situation is as we describe here. Your ship or your situation is always unique. Have I said it is for a fleet analysis only, not a single ship? Well, you can of course use it both, but if you have information on the auxiliary engines of a ship or you know which ships are docking, you can speak to the chief engineer. You have more information on the average power demand, or at least you have the maximums capped, so that is easier to dimension. And of course it is subject to a lot of change, not just the underlying data, but also our formulas, the way of working. Those will change at some point. That's also why we are showing it to you. Even though it is extra content, not premium content, you will see some premium insights into how we work, and that's all because of the changing nature of the subject and the fact that we're constantly improving and remodeling what we have done. Is that a bad thing? I do not think so, because if you want more, you can always sign up to the hub for premium features, all those updates, the downloads and the support you need in order to make your business case. So yes, we will give you a lot of premium information, but if you need the latest ones, you have to sign up to the hub. But first we gotta talk some basics about shore power or onshore power supply in general and power demand of ships. How it works, mostly technically, which standards are involved, different terminologies, etc. This is intended for those who do not really know the problem or ships or power demand, etc. But well, if you're new to the topic, if you're new to shore power, then this is definitely worthwhile. First, onshore power supply. What is it? Well, it can be pretty simple if you think about it. It's basically bringing electricity from the shore to the ship. This is a beautiful picture from ShoreLink. This is a cable management system from ShoreLink that brings the cables that you see with electricity into the ship itself. And yes, sometimes it involves, just like those at home, or well, actually just like those in industrial areas, but these are just very big plugs that in some cases bring a lot of electricity power to the ships. But it can also be a smaller ships, like a ship like this inland waterway vessel in Rotterdam, that are actually connected not just to the grid but also a battery. So it doesn't always have to be grid, it can also be battery powered or grid supported or battery supported, like for example this particular ro-ro that I also worked on for Scone. There we had a battery with an onshore generator, so we could shut down the generators on board the ship, reduce fuel emissions, fuel consumption, emissions, noise, costs, etc. There's many ways to look at it, but ultimately it's about two things. Well, basically it's one thing, bringing power to the ship in order for the ship to do stuff, but it also involves shutting down the engines on board, so we reduce fuel consumption and emissions. Here you can already see quite a few containers, like 1, 2, 3, 4, that we need in order to power such a vessel. So yes, especially for larger ships, there's a lot of infrastructure required. Here we see another project that I worked on. This was for Herema in the Holland Canal in Rotterdam. You can see the person and the sizes involved. These are 5 different houses, or that, well, small e-houses that house 5 megawatt transformers. So electricity from the grid is actually transformed, converted, and then transformed again in order for the ship to receive the amount of power. It can be very complicated, very technical, as you can see. It can be big, but it is not rocket surgery. Ultimately, it's simply plugging into your vessel at the quayside, so that the vessel can do whatever a vessel does. Cruise ship needs to cool or heat people, well, mostly the chambers or the rooms that people are in. If you have a container ship, you need to either refrigerate containers, drop a few, take a few on, etc. But that is what the ship does while at the quay and not propelling itself. Onshore power supply is thus powering a ship at the quayside. We need a few things technically in order to understand what is happening and to name stuff. So let's have a look at the technical basis of shore power first. Here we see a technical isometric picture of grid electricity power flowing from left to right to the ship, and it goes through a few steps. But basically this what you here see is it. There is one big thing in the middle separating the shore side and the ship side. Well, one big thing. Typically it's the cable management system. Everything that stays at shore is what we define shore side. Everything that floats away with the ship is what we call the ship side. That's also how the standards and most people look at it. And the cable management system normally is staying behind unless you have a container ship. More on that later. So we have first grid electricity. Then we have the substation. That's where the electricity comes into the terminal typically, or at least the place where we are in need of electricity. It can be terminal, it can at the quayside, it can be anything, but the DSO, the distribution system operator of the grid, typically more regional, medium voltage, that's responsible for making sure that it all works. It is then brought to the E-house somewhere at the terminal that houses the transformers that you just saw, and typically also in the EU converters, because a lot of ships on the right hand side are powered by 60 Hz equipment, so they have a different frequency as to the European grid, which is on 50 Hz. And of course the power management system also needs to be installed in order to redirect and know where the power is, where to direct power to, the safety, the interlocks, everything else needs to be included there too. Doesn't have to be one e-house, doesn't have to be one substation, can be multiple places, equipment divided, transportable, etc. But this is of course to make it easier. And if we talk about substations, typically we talk where the grid enters the premises. The e-house is what contains all the equipment to power the ship. And then we need the cable management system in order to transfer the physical cable to the ship side. Container ships are the only ship types that are to carry a cable management system on board. Everyone else typically has the cable management system installed on the shore side. Looking into the ship side, so what happens there in order for us to shut down the auxiliary engines that you see on the right hand side. The cables come in to the connection panel. That's where they are physically connected. That's typically a secured area with a latch, and you have high voltage for the ships, medium voltage for the shore, but at least a lot of electricity, so you want to be working in a safe environment. So that's where it comes in. You push a few buttons, you close the hatch, the gates, etc. You check for safety, and then power can be put online. it first or typically flows through a transformer, especially with high voltages. It's not always the case that the voltage coming in is the same as the voltage being used on board the ship, but it always comes to the main switchboard or the main bus bar. You also have one in the E-house, of course. The bus bar is the physical copper part that commingles all the electricity, and then the switchboard is the whole thing around it, including the power electronics to divide the electricity to the places where it's needed on board. So power is coming in, goes to the main switchboard, and once we have the ship connected, the auxiliary engines are typically still running, or you have to do a blackout, but typically we like synchronization. So power is slowly coming online, the auxiliary engines are still running, the main switchboard and the power management system notice it, so it slows down, it reduces power produced by the engines, maybe shuts one off, then the second one, power is ramped up on the shore side, and then at some point engines are shut down, all the power is coming from the shore, and we have a ship running on shore power, and the auxiliary engines are off, we're reducing fuel consumption, we don't have emissions, and no noise emissions as well. And everybody is happy. So that is what shore power is. The technical basis is described in the IEC IEE 80005 standard. This standard is the typical standard when we talk about shore power. It's actually consistent of 3 standards, 1, 2, and 3. And as you can see, this is the basic setup of what a shore power system is, shore and ship, and that's also how it is divided. But there's another very important division that we have to make, especially for this masterclass, which is high voltage and low voltage. Like I said, we have 3, but the first part describes the high voltage systems, and the third part describes the low voltage systems. Big ship, small ship. The second part describes communication systems, safety systems, but mostly communication, and those that is used by both these standards. 1 megawatt plus is typically high voltage, although the correct nomenclature is that it is expected that HVAC systems will have practical applications for ships requiring 1 MVA or more, or ships with high voltage main supply. So it really depends, but once you get to the megawatt level, or actually a lot less already, at 6 or 500 kilowatts, you might want to use higher voltages in order to get lower cables and easier access to the power itself. But high voltage systems typically above 1 megawatt, 6.9 or 11 kilovolts, and can both be 50 and 60 hertz. And then we have below 1 megawatts, typically lower voltage systems, 400, 440, 690 volts typically, and 50 and 60 hertz. I gotta say, I've done both, quite a few. Currently we mostly focus on high voltage systems because these are bigger ships that are targeted by more regulations. Lower voltage systems, in fact, sometimes if you have 400 or 440 volts, you can actually get away with available industrial sockets, plugs, or solutions that are at the terminal side already. But of course, that really depends on the ship, category, type, etc. But suffice it to say, this is another big division, high voltage, low voltage, and it really does impact your design, especially the kilovolts, transformers, etc. that you need. The power itself that you need, of course, is still the same, because you have a ship, it needs a certain amount of power. It doesn't really matter which regime you follow. Another thing we have to discuss, and those are the plugs. Here we keep the same high voltage and low voltage division, because which plugs do we need? Typically this is a big problem in the industry, and that is because these standards do not prescribe which plugs are to be used always. For the high voltage systems, there's only 5 ship categories or types that have been defined as per the annexes, and there you get a prescribed socket and plug for that specific ship type. For the lower voltage systems, it's only 3, so only 3 ship types have been defined. Container ships, if you have a container ships, you know what to do. If you have an offshore ship above 1 megawatt, then, well, you can't really pick and choose. There's a, depending on your system on board, there's a few preferences. And those are described in different annexes, especially the sockets and plugs annexes. So there is absolutely a preference for specific sockets and plugs, even if it is not normative or prescribed, but people get jumpy if it's a choice, and that choice might be changed later, and these standards are also being changed. So yeah, it's a challenge to get the right plug if you don't have a ship type that's in here. However, speak to the sockets and plugs providers. Well, they are of course more than happy to give you a plug, but you can always exchange them if needed, especially the geometry. If the back end of the system, the electronics are okay, then it can be changed. So it's a challenge, but it's typically not a technical challenge, but more a commercial challenge. So then, you might think, what's the problem here? Do we have a problem? Or should we start with, why is this suddenly a thing? Well, one more thing before we dive into the power demand itself. Here we see the regulatory framework, a picture made by EMSA, so the European Marine Safety Association. And well, there's a lot of stuff going on. Two things are very important: fuel U for the ship owner, AFIR, or the Alternative Fuel Infrastructure Requirement Regulation from the EU both. They prescribe ship owners, container ships and passenger ships to use shore power from 2030 onwards, and AFIR requires port authorities to have 90% of all port calls electrified, certain ports, by 2030, more ports by 2035. So these really drive the uptake of onshore power supply, and this is the reason why shore power is more a hot topic. Thirdly, and this is just EU, I know there's a lot of stuff going on in China. I know there's stuff going on in China, but they have a lot of shore power as well, but it's harder for us to take in. There is another regulation pushing for shore power use. That's the ocean-going vessels at berth regulation in California. That's been going on for quite a while. And these regions really drive the uptake for shore power. And that's why it's important, because if you have a ship and you want to have it continue to sail in these areas, especially container ship and a passenger ship, but also other ship types are benefited by the use of shore power under the fuel U regime, then it is very important to have shore power, or to at least look at it. The problem really is that most people, sometimes not even the ship owners, really know how much energy they need. Let me give you an example of the Fortuny and Sorolla in Malaga. That's one of the researchers we use. These are two sister ships, and in this particular report it is mentioned that even they typically differ about 30% in their energy demand or power demand when they are doing exactly the same thing at berth. So if we have a look at power on the y-axis in kilowatts over a certain berthing period, so during a port call, you can see that, well, yeah, we can take the average of this, but is this really representable? If that other ship has a 30% higher or different peak loads or whatever, then, well, it's really hard to make an estimate. And like I said, a lot of the times most ship owners don't really record this information. So if you ask them how much power do you need, they have a look at their maximum and they say, that's what I need because I want to be able to do exactly that. And typically that's an overstatement of twice the average power demand. So this is just to show there's a high degree of fluctuation, not just between sister ships, so typically your clone, but even be of the same ship at different berths. So you might think, yeah, hold on, this is surely calculated, right? I mean, you have an operational profile and you have engines running. Well, yes and no. Of course, you have these load tables of the different operational profiles. As you can see, operating conditions, running times, there are all kinds of estimates on basically stating this is what you would need in terms of kilowatts if you are doing that. But ships, you know, just like houses and people, they evolve, they change. Extra engines are outfitted, new engines. Typically a new crew or a different crew has a totally different impact on energy use. I have some good stories to tell about that. So this is a nice basis to start, but it doesn't give you necessarily what it should be in reality. You always have to talk to the chief. But if you have this, yes, of course, this is a very good estimate, and in the land of the blind, the one-eyed man is king. So this is definitely, if we have it, the first thing we go with. But like I said, power demand is changing during berth. So these are what you saw, the operational profiles, what they should do. Then we have reality, what they actually do. This is taken from a T&O report, and this is the case study where they looked at container ships. And suppose you make calculations for a specific amount of reefers, refrigerated containers that go on board. I mean, that already changes. So if I have a ship that is capable of doing a lot of reefers but not using it, I get a totally different average power demand than a ship that has a lot of reefer capabilities and is typically using it a lot. Then I need to make a different business case looking at the investments needed from a shore strategy. So it's not just the table and how much it would be, but it's also how much do you actually use it in practice. And if you have a container ship that does the one thing 1 year and another thing another year, it's hard to make a few years business case on. So power demand is changing during the berthing itself, during different operational profiles for different ships, for different crews, etc., etc. In fact, it can be quite bad. There can be up to a 10x difference in loading conditions for the same types of ships. Let me show you. Let me show you, by the way, by taking data that we have collected, and what we see here is complicated, but you will see it a lot. On the x-axis we have GT, gross tonnage of the ship. Every ship has a certain amount of gross tonnage. This is a non-dimensionalized or a dimensionless number, so a parameter without a unit that tells something about the size or the inside volume of a vessel. And on the y-axis side we have auxiliary, or actually power demand, the power rating of auxiliary engines installed. And all the green dots, those are all ships in our database of which we have information on the auxiliary engines. The nice curve is the fitted curve. As you can see, a lot of information is above, a lot of them is below, but this is the best fit for this informational fit. Container ships do a better fit, by the way, but we'll show a few of them. And then the fuchsia, actually not the pink dots or crosses, and the box plot that you see also with the crosses, those are either true measured values over time, so real-time measured values, or validated values either by ship owners or onshore consumed power indications. And there you can see that actually, well, let's take this close to Panamax, Aframax, or a medium range band. In this small band, so like ships around 30,000 GTs, we can have a 10 times difference, almost actually high, but almost 10 times difference in installed engine size and thus also expected power rating. So if we have these ships coming at our port, well, what do we have to design for? Well, the peak powers, we can be sure, those can be quite high, 5 megawatts or more. But where exactly is the average? And as you can see, the real-time measured, like a time series domain of these tanker sizes is actually way lower than what is installed on board the ship itself. And that is what we almost always see. Typically, the average power is only a fraction of what's installed, like 20 or 30% max on board the ship. That we can be sure of. So we'll get back to this particular type of graph, because for us that's the main methodology we work for. But we have different ships, twins, crews, also same ships sizes, not twins per se, can have a massive difference in their power demand, average and maximum. And that is not it. Wait, there is more. There are more problems for you, of course. The methodology, the sources, the ship type specifications, etc. It's one big mess. Every source, every organization does it differently. Well, you could argue we will do it somewhat differently as well. But we simply take them all together in order to compare. But let me show you what IMO, DNV and EMSA did. First, well, this is one part of the table that we made that compares container ships and feeders, smaller containers, with different dimensions. So some sources, IMO, use 20 equivalent units, so container feet, for dividing the container ships in terms of low, average and high power demands. And then DNV and EMSA do it by a GT, so there's already a problem of, comparing apples and pears. And then they also have different bands, and actually I can't be certain that what they call a container ship another class does as well. Typically container ships, by the way, they're okay. But general cargo, bulk carriers, combination carriers, so different ships and different categories and types, and also through different frameworks, are called differently, have different units for measurements, have different bands, have different, well, results, so that actually the result here can vary an order of, again, 3, 4 or more. So methodology, sources, ship types, consumption, everything, it's one big mess. But the 3 biggest problems are: the same ship varies a lot in its power demand, up to 300% per or during a port call, even, as reported by some, and also what I have experienced myself with smaller ships and with larger ships. There's a high degree of variation in power demand. That's just it. Now we also have the fact that similar ships that you saw on the same band can have a 10x different in at least installed auxiliary engine power, but therefore also average power demand. So within the same range of ships, you can have a tanker Panamax that's intended for, just loading on, offloading, typical cargo, no cooling or heating functions. Or you can have similar sized ships that have a lot more functionality, need to do stuff on board, have a lot more energy need than those others. And if you have to both, well, accommodate them at berth, then making estimates on the power demand and the equipment you need is a big problem. And then finally, maybe the biggest issue, sources 100% disagree. Like I just shown you, there's a lot of differences in the sources out there. Even if, and this is a beautiful story that I might come back to, even if you have 6 months worth of data, different chief engineers can interpret that data differently. And that's also what you see in all the different sources. Again, in the land of the blind, the one-eyed man is king. Personally, I do believe, and of course physically, there is one average, one value that if you use, at least in your business case, you get a proper estimate of the power demand and the energy need of your ship. But you can only, or typically you can only calculate that in retrospect. Ships change, not just what's installed, but also their operational profile, the crews, what can be done, what they want to do, etc. So you can always calculate it in retrospect, but that's not what we're up to. No, in fact, what we are up to with this masterclass, the guide that we prepared and the database, is to give you all the tools you need to make a proper business case from the perspective of a shore power project developer. So we start with this masterclass, we give you the basics, the IDs, the introductions. You can take them and you can read the guide, go deeper, find actually in the premium version all the formulas, calculations, references, sources, etc. And if then you even need more, you can use the database and the interactive tools in order to make bite-sized or big business cases for your own project. So we give you all the tools you need in order to make the business case for yourself. So in short, if the problem really is what is the average power demand of a ship, we need to start with one thing first, that is, what is a ship? Or actually we know what a ship is, but what different ship types, etc. do we have so that we can properly classify them according to, well, the following few things. We made our own ship classification system, which is called our ship types guide, and here we explain how we do it. Let me show it. On our website we have the ship types guide that you can find. This is the premium version, and here in this ship guide we have our own methodology on defining different ships according to category, types and sizes. It's a pretty long read, 47 pages. Let me just give you the summary. What do we mean by category, types and sizes? Category is for us the most important because it's the regulatory and economic grouping of ships. Most other classification systems out there, including that IHS system or previously IHS, but also IMO, which typically states that there is no such thing as a singular ship type definition, which is nice. We take a look at IMO, EU, other regulations, EXI, CAI, Fuel EU, EU ETS, etc. and we have structured them, we have laid them together, and these are the different categories that you have that most of these regulations, if not all, at least hint to or use, from which costs flow. So for us, these are the categories that we typically use, and we will also use that for the averaging of the shore power demand, because if you have such a category, there are specific costs involved for running that ship from a compliance and sustainability perspective. Then we have ship types, which focus on functional use and design. From these ship types flow power demand functionalities. For example, we can have a tankers category, and within tankers we have currently 5 types defined. We can always do an other category or whatever else we have, but the more information we have, we can always tweak it further. But we can say that a general liquid tanker of the same size, more on that later, will have a different energy demand than an oil and chemical tanker or an oil products tanker or a chemical tanker. So there are differences in functional use and design that will impact how we look at decarbonization measures, but power demand particularly. And this should have no further clarification, because the bigger the ships are, typically the more power they need. There are some ship categories that do not have sizes per se, only types, like offshore and others, and there are some that do not have such a list as tankers, but this is a continuously evolving system, like much, and this is how we classify ships. And then for us, categories are most important. Let me just give you one example. If we have a look at all the possible combinations in the tanker category, with all the different sizes per type, actually some types do not have that particular size, but at least we have the option for it. Then, for example, if we go to the Bow Explorer, it's a tanker category, chemical tanker type, size medium range, MR. And then we can use these in order to make, as you will see in the interactive database web tool, we can quickly see, oh, I have a terminal that mostly has chemical tankers. Oh, then I expect this type of frequency, these ranges of power. Okay, great. And then you can immediately get an estimate or a handle on how big your infrastructure is in order to do the shore power you want. That's the ship part. Now let's go to the power demand part. In general, what we say is that we use a function, a mathematical function, where power is a function of gross tonnage. Basically, that's it. If we have a ship, because every ship has gross tonnage, we can extrapolate the average power demand based on GT. That is our main methodology. But how do we turn this scribbly line with power into an average per GT? Well, we use what we call scaling functions for that. And let me show you how we make them. Let's go back to this beautiful picture first. So we have GT, every ship has GT, and we have installed auxiliary power on the y-axis side. We actually have multiple different kinds of graphs. We have total auxiliary power installed, single largest auxiliary engine installed. We'll show that in the interactive web tool later on. And this graph that you see is the total installed sum of all auxiliary engines on board. We kept it at 6 megawatts. There are some ships that have a lot more installed, but you can already see that there is some sort of maximum going on here. Most ships do not have a total installed auxiliary engine demand higher than 5 megawatts. You also see those distinct sizes, that grouping that I mentioned. So you see that there are not a lot of ships between, well, you have some GT gaps, so to speak. So this is where we start. We simply take all the ships that we have in our database and we group them by auxiliary power installed. Then the next step is to make a best fit through all these numbers, and that is actually what we call our scaling function. So for almost all ships, that's an exponential function of GT. For container ships, as you will see later, that is a polynomial. So to the power of 3, GT to the power of 3. The more information we have, the better scaling functions we will make, maybe even discontinuous functions in the future. You know, we'll keep on improving them, but the basis of the methodology remains the same. We take the GTs, we take the auxiliary engine data, and then we make the best possible fit so that we can say if we have a ship of that size, this will be the expected installed auxiliary engine amount. Okay, but does the ship always use this maximum amount of power, or maximum, as you can see at 30,000? There's quite some ships, well, most of them are below, but there's quite some ships even who have more installed power capacity, so who are actually higher. But again, we're talking fleets, estimates before we actually have the specific ship, so this is the best estimate that we have. So what the next step is that we use certain load factors. So we basically say we have our scaling function and we expect the ship, like I mentioned, to only use half, 30%, perhaps even only 20% of its installed auxiliary engine capacity when at berth. And we do that by taking the real-time measured data, and especially those box plots, that is multifunctional real-time data. And there you see a good example of, okay, I have these crosses. Most of them are, if I'm not mistaken, from Chalmers. That was a survey done by ship owners. They typically tend to overestimate the usage, and there's a big spread. But that real-time measured data, and we have kept out the lowest few and the highest few percentages of observed values, so there's always outliers, but you see that for that particular ship, with respect to our scaling function, we only use a very low percentage of power at a time. So we take an average, but we also take the low and the high band. And what we try to do here is that the average is what we believe best represents the average power demand of a ship. Average meaning if you put in that average value, you get the best value for money for your business case, so that is closest to reality as we can do. There is, as you can see, a slight little conservativity included, but looking at this, so validated ship owner numbers show most of them are actually higher than our average. But if you look at the real-time measured data, which are all for the same ship type, a few, you can see that they're actually closer to the low band, so our low estimate. And the high one, well, if you look at making a business case, I wouldn't go there, because that means that if you are looking for a shore perspective, you're making a lot of money because you're selling more kilowatt hours. I would suggest going maybe to the low band for the low cases and just the average band to, get a base case. But those are the load factors that we do. We have high, we have average, and we have the low load factors. Scaling functions, load factors. And basically that's it. We put in a lot of data, but the power demand of a ship, we say, is a load factor multiplied with a scaling function, which is a function of GT. We say percentiles, estimates, confidence, etc. There are some statistics, but there's no truly statistical analysis in play here that we have used. But that's mostly because, well, we lack the time to do it properly. That will take a lot more time, and we might do so in the future. But also because we know from not just experience, but what we see in the data and other sources, there's no real need to do such a statistical analysis, because then we would be very efficiently doing something that's not effective. But we do say the low, the average, those are the places I would go when developing shore power projects. The high one, that's mostly for engineering and sizing. You could maybe even argue that if a ship has a certain amount of auxiliary power installed, almost always that is because of safety margins, limit cases, or simply the fact that if we have an engine that needs to provide the auxiliary power, we typically need two, because if we just have one and it needs to be serviced, we cannot power the ship. So typically there's a high degree of over dimensioning the auxiliary power demand. Suffice it to say, we have the average, that is our average load factor, and we multiply it with a scaling function per ship category. And if you want, you can even do it per ship type, size, what have you, to further narrow down whatever it is that you need. And we base this all on roughly 7,102 ships in our database that we had information from. It's a bit more now, and 153 either measured real-time data or validated data sets. And again, gross tonnage is used as a metric to make it cross comparable. So let me discuss that validated or measured data. What is it exactly? I'll show it later on in the interactive web tool, but basically it means we have 4 tiers of information. Tier 1 we call installed auxiliary engine data. That's simply the maximum the ship could ever provide. So that's the physical limit, the cap per ship. Then we have measured time series data, which is worth its weight in gold, because that's really what you want. Even so, if you have a lot of that data, that's the story I was referring to. I had 6 months worth of data. I was going to the 2 different chiefs and they both said, that's great, but I want to have A, and the other one said, I want to have 2 times A. So even with perfect data, you're gonna have perfect disagreements. Then we have ship owner surveys that we saw and the regulatory bins that we use because, well, better than nothing, but use those with the knowledge that they are limited in how to use them. Tier 1 and Tier 2, well, like I said, not data is created equal. These are the ones that we base our functions on. The rest we simply, paste them on top of them and see, okay, that looks good or bad, or there's something wrong with the data. Tier 1 is the maximum amount you can get, and Tier 2 is just simply worth its weight in gold for most people. So now we have finally everything we need in order to give some results to you. Let's start with a box plot overview of some of the categories. I like box plots. I don't know why. It's maybe because I worked with them in the past when I did do some statistical analysis, but it gives me a lot of information and confidence. So here we have the average power demand box plots. On the y-axis we see these different categories that we discussed, so tankers, bulk carriers, all the way down to passenger ships, and on the x-axis we have the power demand itself. It's actually cut at about 2200-ish kilowatts. You can see that the bars for ro-ro vehicle carriers and passenger ships, they extend quite a lot. That's because in this graph we simply put down all the calculations and values that we did and we group them. So what does this tell us? Let's take tankers for a benchmark. Of all the tankers that we have, and I have to look up what the GT range is for in this one, but it's in the guide, so I'll show it later. I thought the GT range was up to 50,000 GTs. Of all those tankers, the average power demand, according to the auxiliary engines installed scaling function multiplied with the average factor for tankers, we get 1 megawatt. But 50% of the time, of course, it's below, and we can expect it to be at least always higher than 200 or 300. And 50% of all observational data is within those blue squares. So that is where we get our low, average and high from. And if we take general cargo ships, for example, we can say with a very high degree of confidence that the average is only 160 kilowatts, and it's all very close together. So there's no need to do very big statistical analysis. It's all pretty close. For ro-ro vehicle carriers, cargo ships, passenger ships, especially cruise ships, which are not even in here because we had only 40 data points for those, they have an extreme high range. You can see that they well exceed 2000 plus kilowatts in their 50% confidence band, and then there's also that 25% extra. So there is really a very good incentive to go deeper into the ship itself. But if we have a tankers or a container ships terminal, unless we have information that very big ships are coming, we can quite easily say that until that range we have this as our average power. So these are the numbers that we use for our analysis in order to make business cases, revenue estimates, etc. But let me show you the overview of all ships and also tell you that the functions are fudged. So they're changed a little bit because it's premium content and it can only be used as a fleet approach. We have those 7,000 vessels with auxiliary engine data, but if we don't know which ship is mooring, then we don't know what is what. So we use this, like I said. So if we have a ship or multiple ships, we first have a look at the category, we input the GT, we have as a result, then we have in our output directly the estimated power demand, low, average and high. And that is done for all the different ships. Back to that beautiful image again. This is for tankers only. And there we have just per GT, we can estimate, all right, that's how good we can get. Typically, well, as you can see, there is always a very high degree of uncertainty, but the more ships you take, the less that uncertainty becomes. And that's the beauty of this approach. That's just the law of larger numbers. And I know this is a lot of information because it's taken me years to digest, and it's continuously being updated. So let me show you the place where you can download everything you need. In the average shore power demand guide, that is where you will find all the information that we have just now discussed and more. This is the premium version, so a few things have been blocked, but this is basically the data dump in a single PDF that you can download and use for yourself. So there's a lot of, well, there's some information in the freemium that is blocked, mostly the formulas, the functions, the scalings, some of the results, etc. But have a look and see if this is anything that you can use yourself. What is way more fun to work with is, of course, the average shore power demand database itself. And here we see the freemium version as well. We'll see how far we go because the premium has a bit more features, but it's premium, so I can't show everything. But suffice it to say, all the information that we have, we put into a database, and I'll show that later as well. And that you can use to make your own estimates. So what do we have here? So here's the business end. We can do a few different visualizations. So we can plot GT versus average power, and these are exactly those scaling functions that we described. We think that for ship category tankers, this is the thing to look at. I mentioned that bulk carriers and offshore. Yeah, I'm gonna cheat a little bit. Let me get you the premium tool. And that's because I wanted to show you the container ships. So when we select container ships, you can see our scaling function differs a little. And that's because if you have a look at all the single installed engine, it is different than all the other ship types. And well, every ship type, category, blah, blah, has its own curve, one could argue. But this was for us the best fit. So these are all the single highest installed auxiliary engines. So for example, the biggest one, let's see, the MSC Maya, almost 200,000 GTs. The single largest installed engine on board is 5,500 kilowatts. And that's big. Even if we use a few percent, 20 or 30% of that, we still get a high power demand. So these are the big ships, but you can see this one is, well, it's having a nice spread. So we can say with more confidence something about the data. We also do it for the total installed auxiliary engine on board, and luckily that is very similar and should be. And this is also a pretty nice distribution. Here we can see this distribution of the single largest installed auxiliary engine on board. And this helps me to determine, for example, if we have a selection of ships coming to a terminal with the question, do we need high voltage or lower voltage? Here you can see, oh yeah, here we definitely need high voltage. But suppose we have a terminal that only has a maximum capacity of 50,000 GTs. Let's see what happens then. Well, about 50% of the time we could be, 40%-ish. 40% of the time, roughly, we are at lower than 1 megawatt and the rest is higher. So I'd still choose high voltage. But who knows, could be different. And this is the single largest. If we look at total auxiliary power installed, I know for a fact that most container ships have quite some overcapacity or multiple auxiliary engines installed because of that reefer system or thing that we discussed. So yeah, even here, and I know for a fact that 8 megawatts is prescribed in the standards as power requirements for a high voltage. So that, yeah, that's pretty much what we see in the data as well. Container ships only has one ship type. So, but if we go back to tankers, and I want to show them also 200,000 ships. Yeah, 2 has only 0. Here we get the automated numbers. Suppose we want to have a chemical tank, crude general, or oil and chemical. Let's see it. Oh, these are pretty small actually. That's nice. So we see if we only have an oil and chemical terminal, well, we have some outliers here, but most of them, whoa, hold on, they're pretty close. So let's see if we, if we change here to a different sizing, then we can see most of them are Panamax, no, small. some small. Suezmax, none. Oh, sorry, I'm going the wrong way. Aframax, we had handy size. Yeah, handy size and medium range. Most oil and chemical tankers are thus this size. So if we go back to all different ship sizes, yeah, that covers most of them, which makes sense because of their functionality. So this is how you can use the different aspects of the database, and there's multiple things that are two things that I want to show you. The voltage and frequency, which is also important. Well, frequency almost always 60 Hertz, but here you can have a look at what types of ships are there, medium range and handy size. Okay, well, that figures, that's what we saw. 440 volts and 450 volts. Well, that also figures because according to the standard they have to be 440. 450, 440, that doesn't really matter. 400 still, okay, 380, okay, well, you know. Probably we need an installation that is 440 volt. Apart from what the standard is saying, most of the ships can accommodate that. And 60 Hertz, so if we are working on the EU, we need some sort of converter. And then finally, before we go into the real database, here we see, after some loading, it can be quite slow because we have so much information. In here we see all the different ships in our database form. So you know, we can search something. Let's see, we saw something with MSC. How many chemical tankers does MSC have? Maersk. Let's see what it does. We have to wait again because searching through everything. Maersk. Okay, just a few. They are all the Maersk ones. Okay, so suppose I have a terminal for Maersk, then, well, my average would be 1.16. So I would estimate, well, around 1 megawatt of average power for these types of ships. And that's how you can use the database. And this information is all included in our database itself. It's spreadsheet Excel based for the most part. And there's one thing I didn't show you, which is the real-time measurements. If you really want to know more about the database itself, have a look at our tutorial. I just wanted to show you the measured data. So of a few ships, we have measured and or validated data. So that is tier 1 and tier 2 and or tier 3 data with, as stated, some of the measured operational profiles. I should say those are actually here. Real-time measured data or validated data that we can share in this particular form, and or data that we have used in order to make averages based on statistical information. That's what we get our box plot and whiskers from. And this data is included in the database as well, apart from, of course, all the data of all the ships that we have in order to make better analysis of the ships themselves. And this can be used for the ultimate analysis in order to get all the information you want, need, or could possibly require. So you can use it freely in the freemium version. You can download it as a premium member, premium yearly member, or you can simply purchase it as a one-off. But that's enough sales talk. Let's go to the final part, the frequently asked questions. Plus, of course, show you some of the references we have used and still are using in order to make these updates. But first, some key questions that we hear a lot. We have prepared 6 questions and we'll just go through them from top to bottom. First off, what about direct drive versus electric or diesel electric? Oh boy, I hoped you weren't asking this question. No, honestly, this is one of the gaps, I believe, in the methodology that we have to improve. What we have right now is most of the ships, not all, especially within offshore or specific ship categories, there are most likely diesel electric ships that we have not classified yet as such. For diesel electric or electric drive ships, we assume that every engine is basically an auxiliary engine. They're all used for specific operational purposes, so there is not that distinction between the main and auxiliary engine. Direct drive there is easier. We can assume that the main engines are used for propulsion and the auxiliary engines are used for everything else at quayside. Then there's also power uptake or offtake, etc. This we will improve in the future. Right now, 95% of all the information is direct drive, so that is the main focus of our area. Have you used real-time measured data? Yes, as you just saw, we do, but we only have 150 plus data points. of which only about 20 or 30 are real-time measured, as opposed to validated information by the ship owner. We still included validated information because, well, that is something in the very least you could hopefully make a business case on, or if you talk to a ship owner, that will be the answer that a ship owner gives you. And the real-time measured data, said in the beginning, is very scarce. So that's why we don't have it much, but we are working on it and will hopefully provide you more in the future. Why do you use GT and not containers, deadweight, or all the other kinds of fun nonsense that the others use? Well, that's because if you use only GT, you can compare. Tankers typically do not have containers on them, or containers do not really use deadweight as a metric to see how much they can carry. Not at least, well, for fuel, but that's a different story. Every ship has a GT value above 400 GTs. So with that, you can easily calculate and compare. It does give other problems because all the bands that you saw that do use something else as opposed to GT, we cannot use them, or we need to convert them into GT. We also did that in the guide itself. So benefit, some challenges, but GT, at least every ship has them, so we can use them. Which load factor should I use when making a business case? All of them, and mostly the average one. Like I said, there is one average that you can use for the perfect business case, which can always be calculated in retrospect. But in the land of having only a few % of the information to make a business case, just use the average. Use the lower band in order to get low conservative estimates, and the higher band if you want to pop out the champagne, or if you are dimensioning for the maximum power outputs. But of course, if you have a single ship, use the auxiliary engine rated power as maximum, and then use average power for the revenue estimates. This is a nice bridge to the second one. What about fifth? What about maximum power demand? Ah, yes. Like I said, the physical limit for any ship is the auxiliary engines installed. For direct drives, it can be all of them, but typically they don't use all their engines at the quayside, so it's 1 or 2. And for auxiliary or direct drive, normal ships, it's typically 1 or 2 engines, unless we have ship types such as container ships and tankers, which use more auxiliary engines typically because they do a lot of stuff at the quayside. We saw general bulkers only using a very small percentage of power compared to the total, but the maximum power demand, if we have a ship, if the ship is known, is just the rated power of the engine, if not the high band, or just take 100%, so the scaling function itself as the maximum power demand. How do you get this data, or how did we get this data, and how do I get it? Well, you can buy it from us, of course, but let me show you where we got it from. If you go back to the database again and you scroll down, you can see the average shore power demand guide. You can download it, or you can just open it here and scroll through it. Members can download this one, and if you scroll through the executive summary, you will see a references table. There you go, with all the references that we used. Of course, we took some of these references and included the underlying data into our reporting, but let's have a look at one of the most cited pieces of research when it comes to shore power. That is I was thinking the Carp Ocean Going Survey, yeah, that one too, but I was actually referring to ABB Chalmers. That is this one, a master thesis already some time ago, which a lot of the other sources also use or refer to. Actually, we made a comparison in this guide of all the different sources, and there you can see the underlying data and how we used it, etc. So even here, let's see, yeah, this is a lot of scrolling. Yeah, so these are the key resources and sources that we used in order to really tweak and finalize our data. And then in the future, of course, when we get more real-time measured data, we will tweak the scaling functions, add to the functionalities in order for you to get a better estimate of the average power demand. And that's it. Enjoy the light reading. And if you want to have the information yourself, the databases, the guides, or the expert premium support at your fingertips, if you need more, all you got to do is sign up to the hub. Go to our website, sign up, and we can get you started today. Thanks for watching the video and have a great day.